going to talk a little bit about I'm going to talk about a different problem that is called the facility location problem, and this problem is actually quite related to clustering, and we will be see this in a minute. Okay, so the idea of this problem is that we have a set of potential locations for the facilities. Okay, let's take this one, this one, this one, and this one. And then we also have a set of customers or users. Okay, for example, this is a user, this is another user, and so on and so forth. And then we need to create a mapping between the users and the facilities. You can imagine that the facilities are the location of the facilities. You can imagine that these are the potential locations for creating new hospitals. Okay, and then we need to identify the optimal location of the hospital in a way that the customers are close to the facilities. Okay, so we want to minimize the total cost of serving the customers. Okay, and that could be the total distance between the customers and the facilities. Basically we have to take into account that we can only create or open K facilities. Okay, so that's the idea that we want to have. We have the input is going to be we have a set of facilities and we have a set of customers, and then we need to decide a subset of the facilities, let's say K, that are going to be providing service to the customers in a way that we want to minimize the cost. Okay, so we can see that uh, this is going to be a clustering problem. Okay, so we need to create the clusters around those facilities that we open, that we create. And for example, if this is the input of the problem, we can create these clusters in this way. For example, if we say that k is equal to 3, then we can say that this is one of the clusters, this is the second of the clusters, and this is the third of the clusters. Okay, so something important here is that in the facility location problem, we need to have that this point, the representative point, we call this a representative point, is going to be must be a member of must be an object or a sample that we have in the data set. Okay, for example, and that's going to be the difference between this problem and the k-means problem. In the k-means problem, the representative point of the object is not an object that we have in my sample set. It's the center. Here, the representative point is going to be one of the indicated points for the facilities. Okay, and this is actually a small version of what we call the K-Medoids problem, the K-Medoids clustering problem. Okay, and basically this is going to be the formal description of this K-Medoids problem. Okay, basically what we're going to say is that we have a set of points or samples or objects. Okay, and we have d dimensions. Basically, this is the number of features that we have. Remember that this is a unsupervised learning problem, and we don't have that. We have the vector of features, but we don't have this target label. Okay, we don't have that expert that is going to tell me, okay, this is from this category or this is from this other category. And also we are going to have this k, which is similar to the k in k-means. Now the idea is that we're going to have to create these clusters. Okay, basically, and what we have to identify here is that out of these endpoints, we need to identify k points that are going to be the representative points of the of the problem. Okay, and these are going to we are going to call this the Medoids. And we want to minimize all this equation. What this is doing is that we want to minimize that error or distance from the customer from the points to the closest Medoid. That's what we want to do here. And okay, we also call this the algorithm that we use to call this. We call this PAM partitioning around Medoids, and it's actually quite old. It's from 1988. And this is more or less how the algorithm works. It's quite similar to the K-Medoids, the K-means method. Basically, the idea is that initially we are going to be selecting at random K-Medoids. So we have the original data set, and we're going to select random K of these initial points. And then what we're going to be doing, we're going to be saying that these are the initial representative points of my, or samples of my problem. And then what we're going to be doing is that all the other remaining points, we're going to be assigning that to the closest Medoid, to one of these K. Basically what we do is that we compute for each particular additional sample or point, we're going to be computing the distance or similarity to all the Medoids, and then we're going to be looking at the one that is closer. So that's going to be, and then that point is going to belong to the cluster of the nearest Medoid. And then we start trying to change, trying to replace the Medoids. We try to replace one of the Medoid with another one, and then we repeat the process of identifying the closest Medoid. We have to see if we need to change one point from one cluster to another one, and then we repeat this until we cannot improve anymore. So the idea is quite similar to the K-means problem, but now this is the main difference is that the center in the K-means is we're going to be using the representative location is going to be the center of the cluster, which probably is not going, it might not be a point of my, we probably don't have any point in that particular location. And if we relate this to the facility location problem, and then if we use the center of the cluster, for example, to as a representative point, we probably cannot create a hospital there because that might be, for example, in the middle of a mountain, or it could be in a lake. So that's why we need to have these Medoids, and the location of the facilities is going to be in a particular, it must be a particular point of my sample of my problem. In this example here, well, let me see, let me show this with an example of how this example, we can see that we have a set of points. Okay, basically here, in order to show this in 2 dimensions, I'm going to assume that we only have two features. Okay, and then we can visualize this. We can easily visualize this. Okay, and these are going to be the x and y coordinates, and then basically these are all the samples that we have, all the points that we have in my data set. Okay, and basically the idea is that the initial point, the starting point of the method is that we are going to be selecting at random 2 Medoids, because we are going to be saying that k is equals to 2 in this particular case. Remember that this k is a parameter, and we need to know this beforehand. Or we can use, for example, the elbow method or something like that. Okay, so let's say that we initially identify like 2 and 8. These were going to be my initial Medoids. So now what we're going to be doing is that we're going to be creating the clusters, and in order to create the clusters, we're going to be assigning the point, all the other points to the closest Medoid. So basically what we're going to be doing is that we're going to be computing the distance, for example, this distance and this other distance, and then of course we're going to be assigning the point to the closest Medoid. In this particular example, we said that 7 is going to belong to the cluster for this 8. And, and then we are going to be repeating this process multiple times. And then we just take, for example, 1, computing the distance from 1 to 2, and the distance from 1 to 8. And of course, in this case, we will be seeing that 1 is going to be in the cluster of the representative point for the Medoid number 2, and so on and so forth. Okay, so basically, after we repeat this process, we're going to have that we have um, these 2 clusters, and with all these points that we have, based on the closest representative object of the Medoids. And as I said, well, basically, and the error is going to be the distance, or sometimes we call this error. Sometimes we use, for example, similarities. Basically, it's going to be, we're just going to be adding the distance between the points and the nearest Medoid, the closest Medoid. So, for example, we take this distance, and then we're going to add this distance, and this distance, and this distance, and that, and then this one, and so on and so forth. And the idea is to minimize that number, because we want to have the optimal solution. Basically, let's assume that in this particular case, that distance is going to be 20. And then the next step is that we want to try to start improving this solution. And how can we improve this solution? So basically what we're going to be doing is that we have to try to start changing this Medoid with another one. Okay, let's say that now we are going to be saying, okay, what about if I don't want to use 8? What about if I want to use 9? And then we repeat the process of assigning points to and then we are going to be seeing if we have to change points from one cluster to another one, because of course if we apply this, then we are going to be seeing that some clusters must be moving from one cluster, some points must be moving from one cluster to another cluster. And then we compute the distance, and then we repeat the same with another point, and then the same with another point, and so on and so forth. And if we see that we improve, then we are going to be changing the, the configuration of the clusters, and then we repeat this until we cannot improve the distance or the error. Okay, so basically, let's say that we want to replace now 8 with 7. Okay, if we do that, then now we recompute the distances, and now we got that the solution was 22. Of course, I mean, we don't want to move to a solution that is worse, because we want to minimize that solution. So basically, this is not a good idea. Basically, replacing 8 with 7 is really is not a bad idea, because it's not improving. And what we want to do is that we want to improve. So basically, this is not a good idea. So basically, now we have to try to explore another one and another one, and so on and so forth until we improve. And basically, now we will be seeing the different cases when we have to update the configuration of the clusters. Okay, let's say that before this was the representative point, and we want to change this one with the new B. Let's say that before we have this B that is blue as a representative point, and now we want to change that with this red. In this particular case, uh, this P, let's say that we want to explore this one, if we want to replace this point, if we want to change this from the current cluster to the other one. So now what we have to do is that we have to compute the distance between the new point, the new representative object for the second cluster, and the representative distance to the current cluster. In this particular case, we can see that this distance that we have here is certainly better than this distance that we have here. So basically, in this particular case, we don't have, for this particular point, we don't have to do anything. This point is still going to be in that particular cluster. Now, but in other cases, we will have to change the configurations. Okay, again, this blue B is going to be the previous, the current Medoid, but we want to explore if we want to replace this with the red one. Now, if we apply that change, we will be seeing that before this distance here, it was better than the distance that we have to the representative point of cluster 1. If we update this change and we change this point with this new one here, we will be seeing that the new distance is going to be worse. The distance to the for this representative clustering, or this representative point, is going to be bigger than the representative point of cluster 1. So in that particular case, we will have to replace. Now this point P is going to be, we are going to be changing this point P from cluster 2 to cluster 1, because it's improving, and then we will be decreasing the cost of the solution, or the error. Sometimes we call that the error. In this particular case, now what we want to do is that in this particular case, we want to replace the point, but we don't have to change the configuration, but we just say that still this is going to be in this cluster, but we have to assign this to the new Medoid, because it's closer. And this is going to be the last case. In this case, we are going to be moving from P that is in the cluster 1. We need to move that from cluster 1 to cluster 2, because the new representative cluster is going to be better, is going to be closer to this point P, is going to be closer to the new representative point of the second cluster. And then we will be repeating, we have to explore all the possibilities, and then we will be updating the Medoid of the cluster, and then we have to keep repeating this process until we cannot improve anything else. We cannot improve the solution. The idea is quite similar to the to the k-means problem, that the k-means algorithm that we talked before. Okay, so basically, as I said before, this is quite similar to the k-means method. And of course, we're going to be sharing. Okay, it's similar. The process that we follow is quite similar, but we have a little bit of the main difference is that the center is not is in the K-Medoids problem. The center must be a point from my data set. In the k-means, the center is going to be the middle point of the cluster. And I already talked a little bit about why we have in some particular cases that we need to have that particular situation. Now, if you want to implement this, it's basically going to be quite easy. They have one particular library. You have a particular function that is doing all this job for us, and then all we have to do is to call PAM, and then that's going to be doing this job. For this, we need to have this library that is called cluster. Remember that we don't. This is going to be a unsupervised learning problem, so we need to remove the target label, and we also need to identify the k value. And this is going to be basically the process that we need to follow in order to implement in R this, if we want to use the implementation of the partition of the K-Medoids method. Okay, and if you want to, for example, remember that this, we need to know this beforehand. Okay, the value of K, you could use, if you want, you could use the elbow method for this, that I talked in a previous video. Remember that one of the applications of this is a real application. This is called uh, the warehouse location problem, which is basically trying to identify the best possible location for for a number of warehouses that a particular company wants to open. Okay, imagine Tesco, for example, they need to create warehouses, and those warehouses must be close to the shopping centers, the points that they have. And we want to minimize, of course, they want to minimize the cost. The cost, sometimes we measure the cost in terms of the distance to the warehouses, but sometimes it could be something else. It could be a particular metric that they have. And this is, for example, one potential solution. Opening, for example, this one assuming that we want to have the k value is going to be equals to 3. We have very huge data set with millions of points. Okay, in that particular case, implementing this PAM method, this partitioning around Medoids method is going to take a lot of time, and sometimes we don't have that amount of time. So what we are going to, a very popular solution for that particular case when we have a huge data set, a very large data set, is what we are going to be using this approach called CLARA. Okay, it's very particular. It's quite useful if we have huge data sets that we cannot compute everything in a systematic way. Okay, so basically what we're going to be doing here is that we're going to be selecting at random a sample of the points. Okay, let's say that you have 1 million points. So basically, and you have to select that, in that case, you will be selecting a random subset of those points. Let's say that you want to subset, if you have 1 million points and then you want to select 100,000. And then based on that, in those 100,000 points, you will be applying the regular K-Medoids method. You get the sample, and then what you try to do is that you get from that particular sample, you get the representative set of Medoids, and then you finish all the process, you compute the clusters, and after that, the remaining portion, you just will be computing the distance to the closest Medoid from the original sample. And that's one of the alternatives that we use in order to deal with huge data sets.